So until now we have seen the concept of Lebesgue integrals, and we have emphasized particular properties of absolutely integrable or L1 functions. And in this lecture we will come to a new topic, which is that of various modes of convergence, in which a sequence of real or complex measurable functions can converge to another measurable functions on a measure space. So the idea here is to answer the following question is how to give meaning to this to the statement that fn converges to f as n goes to infinity. So as we will see, the answer is that there are various ways to do this, various different ways to define convergence. So this is first part, and the second part is that these ways, different ways or modes, we have also called it modes. So these modes of convergence are may or may not be equivalent. So in general we will have various different ways of defining convergence for a sequence of real or complex measurable functions, and these modes of convergence may or may not be equivalent, meaning that each may be inequivalent to the other. So we will see various examples of such things, but first let me recall what we already know from our undergraduate days. So two basic notions of convergence. So the first one is pointwise convergence. We have already seen pointwise convergence. This is the most basic way of convergence for a sequence of functions, and it says that fn converges to f pointwise on x if and only if for any epsilon greater than 0 and x in x, there exists a number n, a natural number n, such that mod of fn x minus fx is less than or equal to epsilon for all n greater than or equal to capital N. So of course this capital N here, this capital N depends on the point x. So once we have chosen a point, the threshold capital N after which this is valid, this inequality is valid, depends on the chosen point x. Now for uniform convergence, this is another basic notion of convergence. Uniform convergence, fn converges to f uniformly on x if and only if for any epsilon greater than 0 there exists a capital N such that mod of fnx minus fx is less than or equal to epsilon for all n greater than or equal to n and x in x. So this is for all x in x. So the difference between uniform and pointwise convergence is of course that this capital N now does not depend on x, on this chosen point x, depend on x, and this capital N, the threshold after which this inequality holds, can be chosen uniformly over all points x in your space X. So an example of a function which converges of a sequence of functions which converges pointwise but not uniformly is the following. So if you take fn x, so fn, let me take the real line, and our functions are real valued, measurable, and we can define fn x to be x over n. So this is for n greater than or equal to 1, and so this is a sequence of functions, so easy to check that fn converges to 0, the function 0, pointwise but not uniformly. We have seen that even if it is not uniform, it can be locally uniform, and in this case we do have local uniform convergence. So but does converge to 0 locally uniformly. So meaning that it converges uniformly to 0 on each bounded subset of R. So this is a standard example of a sequence of functions which converges pointwise to a certain function but does not converge uniformly. On the other hand, we have already seen pointwise convergence almost everywhere, pointwise convergence almost everywhere. So we say that fn converges to f pointwise almost everywhere if and only if fn x converges to fx for mu almost every x in X, meaning that outside of a null set, which means that fn converges to f pointwise outside of a null set. Or a mu null set, meaning that the measure of the points on which fn x may not converge to fx has mu measure 0. So of course pointwise convergence implies pointwise convergence almost everywhere, this is trivially true, and of course uniform convergence also implies pointwise convergence. So we have sequence of implications for these three modes of convergence. So this is that uniform convergence implies pointwise convergence, and pointwise convergence implies pointwise convergence almost everywhere. We have already seen that we cannot have the reverse implication here, meaning that pointwise convergence does not imply uniform convergence, and it's also quite easy to see that we also do not have reverse implication here. By just modifying a sequence of functions which converges pointwise everywhere on a set of measures 0, we can easily construct pointwise convergence almost everywhere which does not have pointwise convergence everywhere. For example, so for this one, we can take this sequence of functions on R, x over n, fn x is x over n, x in R, and we can leave out just one point, let's say the point 1, and we can take the sequence minus 1 to the power n if x equal to 1. So meaning that fn x is the same function x over n if x is not 1, and it is this sequence minus 1 to the power n if x equal to 1. And of course, when x equal to 1, there is this sequence minus 1 to the power n does not converge to 0. In fact, it doesn't converge to anything. And if x is not equal to 1, then it converges to 0. So outside of a single point which has measure 0, we see that we have pointwise convergence, but it does not converge to anything on this set of measures 0, which is the point x equal to 1. Now we have also seen another mode of convergence, which is convergence in L1 norm. So we say that Fn converges to F in L1 norm if and only if this difference of Fn minus F, the L1 norm of the difference, goes to 0 as n goes to infinity. Now, if you want to compare convergence in L1 norm with uniform convergence or pointwise convergence or pointwise everywhere convergence, then neither does each of these imply L1 convergence, or L1 convergence implies each of these uniform pointwise or pointwise almost everywhere convergence. So we have already seen, for example, the typewriter sequence. So let me make it a remark here. L1 convergence in L1 norm, we will also call it sometimes L1 convergence, does not imply uniform convergence, pointwise convergence, or pointwise almost everywhere convergence, and vice versa, meaning that all these three may not imply L1 convergence. So we have seen the example of typewriter sequence. So this was the sequence of functions on the real line again, which was given by Fn was the indicator function of the set 2 to the power n minus 2 to the power k over 2 to the power k, n minus 2 to the power k plus 1 over 2 to the power k, whenever 2 to the power k is less than or equal to n is less than 2 to the power k plus 1 for some integer, for some positive integer k. So this is for n greater than or equal to 1. So this sequence, as we have seen, actually we can also take 0 1 here, 0 1 to 0 1. These are all subsets of the interval 0 1, and it only takes values 0 and 1. So we can restrict to restrict our functions fn to this interval 0 1 and taking values in 0 1. So we have seen that these functions fn march across this interval 0 1 back and forth, and so it does not converge to 0 pointwise everywhere or pointwise almost everywhere or uniformly, but Fn converges to 0 in L1 norm. This is because the support of these functions fn have a smaller and smaller measure as n goes to infinity, and so it goes to 0 in L1 norm, but it does not converge to 0 pointwise everywhere, or pointwise almost everywhere, or even uniformly. So this is the standard counterexample for a sequence of functions which converges in L1 norm but does not converge in either of these three standard ways of convergence. It is also quite easy to come up with examples in which you have pointwise convergence but not in L1 norm as well. Now, before we see other modes of convergence, it's very useful to keep in mind some class of examples which violate one or the other modes of convergence, and these are called escapes to infinity. So the first one is escape to horizontal infinity. So all of these are examples on the real line. So these are sequence of functions on the real line. So the first one is escape to horizontal infinity. Here we take the function sequence of functions defined by the characteristic function of the interval n plus 1. So this is a sort of moving bump, if you want. So here is your point n, here is n plus 1, and fn is 1 at these points at within this interval, and it is 0 elsewhere, and as n increases this goes to infinity. So it's like a bump moving horizontally to infinity, and we can say what kind of convergence fn satisfies. So first of all, fn converges to 0 pointwise, and therefore pointwise everywhere, almost everywhere, but fn does not converge to 0 uniformly or in L1 norm, because because the functions are 1 at some interval, so the uniform convergence is invalidated, and the L1 norm of this function fn is simply 1 for all n, therefore it does not go to 0 in L1 norm. So we see that fn goes to 0 only in pointwise and pointwise almost everywhere, but it doesn't go to 0 in uniform convergence or in L1 norm. Another escape to infinity is escape to with infinity. In this case, we take fn to be the sequence of functions 1 over n chi of 0 n, so indicated function of the interval 0 n. So here you have this interval 0 to n, and the height of the function is 1 over n. So this is 1 over n, and so we have that it cannot converge to 0 in L1 norm, but it does converge to 0 pointwise, and in fact it converges to 0 uniformly. So fn converges to 0 uniformly, and thus pointwise and pointwise almost everywhere. But Fn does not converge to 0 in L1 norm, because again the L1 norm is 1 throughout the sequence, so it does not converge to 0 in L1 norm. But if you want to bound the modulus of Fnx, this is simply the modulus of chi 1 over n chi 0 n x, and because this is less than or equal to 1, this whole thing is less than or equal to 1 over n, and so this implies uniform convergence over all of R. So we see that it converges uniformly but not in L1. So this is the escape to width infinity because the height goes to 0 but the width goes to infinity. This goes to infinity. Another mode of convergence is escape to vertical infinity. In this example, we take Fn to be n times the indicator function of the interval 1 over n to 2 over n. So again, this is these functions are defined on R with values in the positive reals, and we see that Fn converges to 0 pointwise, and therefore pointwise almost everywhere, but Fn does not converge to 0 in L1 norm. This is because the norm of Fn, the L1 norm of Fn for each n, this is equal to 1, because the width of this interval is 1 by n and you are multiplying by n. So the L1 norm is just the integral or the area under the curve if you want, and this is 1 for all n greater than or equal to 1. So it does not converge to 0 in L1 norm, but also Fn does not converge to 0 uniformly over R. This is quite easy to see as these values n become larger and larger, so you cannot have a uniform bound over all of R. So this is called escape to vertical infinity, because we have these Fn's are of this sort, where you have 1 over n, 2 over n, and the value is, this value is n, and so the height, vertical height goes to plus infinity, while this bump moves towards smaller, the width becomes smaller and smaller, so this length becomes smaller and smaller as n increases. So for example, for a higher n it could be like this, and it goes towards 0. So even though the width decreases, the height goes to plus infinity, which causes problems in the L1 norm and uniform convergence. Now we will define 3 more modes of convergence. So the first one, rather this is the 5th mode of convergence. We have already seen 4. So this is the 5th one. This is called convergence uniformly almost everywhere, or essentially uniformly. So we say that Fn converges to F uniformly almost everywhere, or essentially uniformly, if given epsilon greater than 0, there exists an capital N such that mod of Fn x minus Fx is less than or equal to epsilon for mu almost everywhere x in X. So this condition for uniform convergence is now replaced for by the condition that it only holds for x outside of a null set in capital X. So this is uniform convergence almost everywhere, or what is called essentially uniformly convergence essentially uniformly. So this is the first one in our extra mode of convergence. The second one is as follows. This is called almost uniform convergence. So the terminologies are quite similar, but the behavior is quite different. So one has to be very careful when considering these terms, and one has to be sure of what the definition of these terms are. So almost uniform convergence means that Fn converges to F almost uniformly if and only if given epsilon greater than 0, there exists a set E, a measurable set E, which belongs to the sigma algebra B. This is the sigma algebra B, such that the measure of E is less than or equal to epsilon, and Fn converges to F uniformly on E complement, meaning that the restriction of Fn to E complement converges to the restriction of F to E complement uniformly. So this is almost uniform convergence. And the third one is convergence in measure. So Fn converges to F in measure if and only if given epsilon greater than 0, the sequence of numbers let's call it an, given by, so this nth term in the sequence is given by the measure of points in X such that Fnx minus Fx, the modulus, is greater than or equal to epsilon, converges to 0 as n goes to infinity, meaning that the limit as n goes to infinity an, this is equal to 0, where an is given by this formula. So here note that this epsilon in this sequence, this epsilon is fixed, and so once you fix epsilon, you get a sequence which depends on this number epsilon. So here also this sequence depends on this number epsilon, but as n tends to infinity, this sequence goes to 0, and this should happen for any epsilon greater than 0. So for different values of epsilon you will get different sequences, yet all these sequences has limit 0. So this is called convergence in measure.